All right, this is a daytime reading. Still section 1, theory of heat, page 34. The formula for Boyle's law is as follows. P1 times V1 equals P2 times V2, where P1 equals original absolute pressure, V1 equals original volume, P2 equals new pressure, V2 equals new volume. For example, if the original pressure was 40 psi and the original volume was 30 inches cubed, what would the new volume be if the pressure were increased to 50 psi? We are determining the new volume. The formula would have to be rearranged so we could find the new volume. So V2 equals P1 times V1 over P2. V2 equals 40 psia times 30 inches cubed over 50 psia. So V2 equals 24 inches cubed. Charles' law. In the 1800s, scientist Jacques Charles made discoveries regarding the effect of temperature on gases. Charles' law states that at a constant pressure, the volume of a gas varies directly as to the absolute temperature, and at a constant volume, the pressure of a gas varies directly with the absolute temperature. I'm going to read all that again. Charles' law states that at a constant pressure, the volume of a gas varies directly as to the absolute temperature, and at a constant volume, the pressure of a gas varies directly with the absolute temperature. Stated in a different form, when a gas is heated, and if it is free to expand, it will do so, and the volume will vary directly as to the absolute temperature. If a gas is confined in a container that will not expand, and it is heated, the pressure will vary directly with the absolute temperature. This law can also be stated with formulas. Two formulas are needed because one part of the law pertains to pressure and temperature, and the other part to volume and temperature. This formula pertains to volume and temperature. V1 over T1 equals V2 over T2, where V1 equals original volume, V2 equals new volume, T1 equals original temperature, T2 equals new temperature. If 2,000 cubic feet of air is passed through a gas-fired furnace and heated from 75 degrees Fahrenheit, room temperature, to 130 degrees Fahrenheit, what is the volume of the air leaving the heating unit? See figure 2.11. Okay, so V1 equals 2,000 cubic feet. T1 equals 75 degrees plus 460 degrees Rankine. Sorry, I meant to say 75 degrees Fahrenheit plus 460 degrees Rankine equals 535 degrees Rankine absolute. V2 is unknown. T2 equals 132 degrees Fahrenheit plus 460 degrees Rankine, which equals 590 degrees Rankine absolute. We must mathematically rearrange the formula so that the unknown is alone on one side of the equation. So V2 equals V1 times T2 over T1. V2 equals 2,000 cubic feet times 590 degrees Rankine over 535 degrees Rankine. V2 equals 2,205.6 cubic feet. This result shows that the air expanded when heated. It is important to note that, in the previous calculation, the temperatures were converted to absolute values in order for the results to be meaningful. The following formula pertains to pressure and temperature. P1 over T1 equals P2 over T2, where P1 equals original pressure, T1 equals original temperature, P2 equals new pressure, T2 equals new temperature. If a large natural gas tank holding 500,000 cubic feet of gas is stored at 70 degrees Fahrenheit in the spring, and the temperature rises to 95 degrees Fahrenheit in the summer, what would the pressure be if the original pressure was 25 psi G in the spring? So P1 equals 25 psi G plus 14.696 atmospheric pressure, or 39.696 psia. T1 equals 70 degrees Fahrenheit plus 460 degrees Rankine, or 530 degrees Rankine absolute. P2 equals unknown. T2 equals 95 degrees Fahrenheit plus 460 degrees Rankine, or 555 degrees Rankine absolute. Again, the formula must be rearranged so that the unknown is on one side of the equation by itself. P2 equals P1 times T2 over T1. P2 equals 39.696 psia times 555 degrees Rankine over 530 degrees Rankine. P2 equals 41.57 psia minus 14.696, which equals 26.87 psig. Okay, now this is Unit 2, Matter and Energy. In this example, both the pressures and temperatures were converted to absolute values for calculation purposes. Once the calculation was completed, the answer was converted back to a gauge pressure. General law of perfect gas. A general gas law, often called the general law of perfect gas, is a combination of Boyle's and Charles' laws. This combination law is more practical because it includes temperature, pressure, and volume. The formula for this law can be stated as follows. P1 times V1 over T1 equals P2 times V2 over T2, where P1 equals original pressure, V1 equals original volume, T1 equals original temperature, P2 equals new pressure, V2 equals new volume, T2 equals new temperature. For example, 20 cubic feet of gas is being stored in a container at 100 degrees Fahrenheit and a pressure of 50 psig. This container is connected by a pipe to one that will hold 30 cubic feet. Let's read that again. This container is connected by pipe to one that will hold 30 cubic feet for a total volume of 50 cubic feet, and the gas is allowed to equalize between the two containers. The temperature of the gas is lowered to 80 degrees Fahrenheit. What is the pressure in the combined containers? So we'll go P1 equals 50 psig plus 14.696, which is atmospheric pressure, or 64.696 psia. V1 equals 20 cubic feet. T1 equals 100 degrees Fahrenheit plus 460 degrees Rankine, which equals 560 degrees Rankine. P2 is unknown. V2 equals 50 cubic feet. T2 equals 80 degrees Fahrenheit plus 460 degrees Rankine, which is equivalent to 540 degrees Rankine. Okay. The formula is mathematically rearranged to solve for the unknown P2. P2 equals P1 times V1 times T2 over T1 times V2. P2 equals 64.696 psia times 20 cubic feet times 540 degrees Rankine over 560 degrees Rankine times 50 cubic feet. P2 equals 24.95 psia minus 14.696, which is atmospheric pressure, which equals 10.26 psig. Dalton's law. John Dalton, a mathematics professor, made the discovery in the early 1800s that the atmosphere is made up of several different gases. He found that each gas created its own pressure and that the total pressure was the sum of these individual pressures. Stuffy nose. Okay. Officially called Dalton's law of partial pressure. Dalton's law states that the total pressure of a confined mixture of non-reacting, inert gases is the sum of the pressures of each of the gases in the mixture. Consider two containers, each with a volume of 1 cubic foot, with one containing oxygen and one containing nitrogen. The pressure of the oxygen is given to be 30 psig, and the pressure of the nitrogen is 40 psig. If placed together in a 1 cubic foot container, the total pressure of the mixed gases will be 70 psig, which is brackets 30 psig plus 40 psig brackets. So I think they're timesing it. If placed together in one unit, the total pressure will be 70 psig times, and then it's in brackets, 30 psig plus 40 psig. Figure 2.12. Dalton's law of partial pressures. The total pressure is the sum of the individual pressures of each gas. (2.7) Energy. Using energy efficiently is a major goal of HVAC/R industry. There are many forms of energy, including electricity that drives motors, for example, and heat energy from fossil fuels such as gas, oil, and coal. The only new energy we get comes from the sun, in the form of radiant heat striking the earth. Most of the energy we use is converted from something already here, example, fossil fuels. The conversion from fuel to heat, for example, is accomplished by the burning or combustion process. In a gas furnace, fuel is burned in a combustion chamber, and heat from combustion is transferred to circulated air by conduction through the walls of the furnace's heat exchanger. The heated air is then distributed throughout the heated space. This energy conversion is referred to as a direct process. An example of indirect energy conversion is a fossil fuel plant. Gas may be used in the power plant to produce steam that turns a turbine to generate electricity. The electricity is then distributed by the local power company. This electrical energy can then be converted to electric heat. All right, almost 13 minutes. That's 2 pages, page 34 and 35. Thank you so much, and maybe I'll see you guys tonight.